All right, so the first thing, you, shut it. Okay, this is my time to shine. No lab this week. I will be there at lab time. If you have questions about problems or anything like that, I could answer them. So that's the first thing. The second thing is no class on Thursday, no school at all on Thursday. So don't try to come here. It'll be locked. I don't know. Maybe it'll be open, but there's no classes. Yes, that's the third thing. That's a buzzkill. So next week in lab is the second lab exam. Yeah, not very many. It might just be 2. But it's cumulative, so be sure you go back and understand the stuff from the first one.
When are we finding out our grade on this test?
I will have it back for class next Tuesday. Besides that, I'm not sure. You can't wait that long? I mean, yeah, I'll post them as soon as I'm done. So we'll see. All right. Any questions about the first 2? I don't think you probably have questions about. That's pretty clear, right? There's no lab and no class. That's not complicated. Anybody have any questions about the lab exam, though? You can go to any, like always, you can go to any lab that works for you to take that. And yeah, remember that it's cumulative. So I think we've had a total of 5 separate labs, and you should be ready for questions in the form of any of those labs. Okay. All right, so now back to kinetics. Last time we introduced Newton's second law. The main equation in this whole class, the most important equation in this class. It says that if you add up all the forces, we'll call that F net, that's equal to the mass of the object. So first you choose an object. What's the object you want to look at? Then you figure out all the forces acting on that object, and that's equal to the mass of that object times the acceleration of that object. And the forces, let's say, fall into 2 categories. The first one is weight, and that's pretty easy to deal with. And the second one is contact forces. So once you deal with the weight, you just look for all the places the outside world is touching whatever you've chosen as your object to look at. And anything that's not directly touching it doesn't produce any force for that equation. And we talked about the weight. So the weight, the force applied by gravity, depends on the mass, and it's equal to the mass times 9.81 meters per second squared down, where G is 9.81 meters per second squared. If your coordinate system is the way it usually is, with the y-axis up, then the weight force is, the weight force is always down, so this is the weight force. And that's in the negative y direction, or you could think of that as an angle of positive 270. And so the weight force is 0, negative 9.81. No, the weight force is negative mg, like that. Okay, so G doesn't have a negative. G is just positive. But if you have a coordinate system with the y-axis pointing up, you put a negative in just because that's the way the vector components work. And most of the time, that's what we're going to have. We'll come up on a couple of topics where we have to use different coordinate systems. One thing that is always a little confusing to people, it'll make sense and then it won't make sense and then you'll get confused and then you'll remember, and then, is what's the deal with free fall? So say you drop a bowling ball and a tiny pebble, and let's ignore air resistance. They fall exactly the same, right? We've talked about that a few times now. But what about the forces? Are the forces the same? No, the bowling ball has a much bigger mass, and so there's a much bigger mass applied to the bowling ball than there is the pebble. So that seems weird, right? Like, they fall the same, but they have different forces. Well, yeah, because Newton's second law says to make the bowling ball accelerate, you need a bigger force. So it all goes back to Newton's second law. So anyways, just remember those as two different things. They do have different forces, and they do fall the same, and those actually don't contradict each other. Okay, so now let's talk about contact forces. That's where we are. And we did the two examples with the guy standing on the scale. I just like drawing this guy. And he has a mass of 50 kilograms. So first, with the scale on the ground, the force applied to him by the scale was equal to 0, positive 490.5 newtons. And then we did a second one where the scale was on an elevator. And the elevator was accelerating up. Whoops. At 2 meters per second squared. And for that one, do you remember what the trend was with the force? Was it bigger or smaller if the scale's accelerating up? Bigger, although that's not really remembering. Yeah, right, that's different. Okay, so let's do basically the same example again, but this time let's have the elevator accelerating downwards. What do you expect to happen here? It's going to be, the force is going to be less. So there's the elevator. There's the scale. I like drawing this guy because, like, every time you do it, he has, like, a totally different personality. It's like, so simple. Like, that's not really what this class is about, though. Okay, so this time it's accelerating downwards at 2 meters per second squared. Here's a funny thing. Is the scale moving up or moving down? Not necessarily. Remember, it's moving the direction of the velocity, and the acceleration and the velocity don't have to be the same. So if it's moving down with an acceleration of 2 meters per second squared, velocity and acceleration are both in the same direction, and it's speeding up, going down. If the elevator is on its way up and the acceleration is down, that means it's on the way up, but it's slowing down. Yes, so if velocity and acceleration are in the same direction, it's speeding up. If they're in opposite directions, it's slowing down. So the fact that the acceleration is down doesn't mean that it's moving down. It means if it is moving down, it's speeding up. And if it is moving up, it's slowing down.
So you asked us the trick question by asking us if it was going down, so we don't know if it's speeding up?
Well, we just don't. When I give the acceleration, and so your mind sort of naturally says it's on the way down. That's not necessarily true. Acceleration, knowing the acceleration doesn't tell you which direction it's moving.
Okay.
So what's the force applied by the scale? So Newton's second law, we'll use a coordinate system with the y-axis up. So the weight is 0 and then negative 50 times 9.81. And then, so we've dealt with the weight force. Now we have to look for things that are touching our chosen object. And the only thing touching him is the scale. So F scale X and F scale Y. Those are the two forces. And Newton's second law says if you add those up, that's equal to the mass of the chosen object, 50 in this case, times the acceleration of the chosen object. What's the acceleration vector this time? Yeah, 0, negative 2. That acceleration is in the negative y direction. So there's the acceleration. And so the components are 0, negative 2. And we can break this up into two different equations. The x components give you an equation. So the x equation says 0 plus f scale x is equal to 50 times 0. 0. And the y equation says negative 50 times 9.81 is 490.5 plus f scale y is equal to negative 100. The x equation says f scale x is equal to 0, and the y equation says f scale y is equal to positive 390.5. And those combine to tell you that the vector f scale, the force applied to him by the scale, is 0 for x, positive 390.5 for y. What direction is that pointing, if you had to draw that vector? Positive y direction, so up, yep. So the force is that way at 390.5 newtons. So if you ever want to lose weight quickly, this is probably the best way to do it. Just accelerate downwards. You got to get on something accelerating downwards. Anybody have a feel for what's the acceleration you would need for the scale to say you weigh 0? That's not a healthy weight, by the way. $9.8, yep, exactly. If the elevator is accelerating downwards at the free fall acceleration, there's no contact force between you and the scale. I mean, you're basically just both falling at an identical rate, which is how when astronauts in training, they need to get used to this feeling of weightlessness, and the way they simulate that is putting them on a plane that for a long time goes through this free fall acceleration, and you have the feeling of weightlessness, even though you're not really weightless. Gravity's still pulling on you just as hard. But everything around you is accelerating, so you feel like you're floating. Apparently, it's a very uncomfortable feeling. Okay. Any questions about that? Yes. Oh, yeah. So that's from the last class. So I didn't go through that today. What? So here's where it comes from. If you look at this example, if that scale wasn't accelerating at all, the acceleration on the right side of this equation would be 0, 0. And so the y equation would say negative 490 plus f scale y is equal to 0. And that would give you f scale y is equal to 490.5. If the acceleration was 0, positive 1, the y equation would say negative 490.5 plus f scale y is equal to positive 100, and that would give you f scale y is equal to 590.5. So what changes that value is the acceleration on the right side of that equation. Any other questions? All right. In these examples, we didn't know the direction of the forces. We didn't know the direction of the contact forces before we solved the problem. We didn't know the direction of the contact forces until we solved the problem. But from now on, we're always going to know the direction even before we solve it, and we're just going to solve for the magnitude of that force. So we'll always know the direction of contact forces bless you, based on the type of contact. And so here are the two types of contact forces that we're going to deal with. The first one is the pulling force applied by cables. You might think of a cable as a pretty specific thing, but when I say cables, I'm talking about pulling with using ropes or strings or chains or anything that pulls, okay? And then the second type of contact force is a pushing contact along a flat surface. And so based on which one of these types of contact forces we're dealing with, we're going to use the rules that I'm going to go into now for the direction. We'll know the direction, and we'll use that in the problems. So I'm going to start with this pulling force applied by cables. And we're going to assume that these cables are massless. Obviously, no cables are really massless, but often their masses are pretty small compared to the other forces you're dealing with, and so you get good results with this assumption. And one thing to keep in mind here, notice all of this is true as long as between the ends the cables only contact massless, frictionless pulleys. Okay, so all of the rules that I'm going to give you work for cables going over pulleys, no matter how many pulleys they are, as long as the cable between the two ends doesn't touch anything else besides pulleys. There could be 1,000 of them, and this still works. So each cable has a tension that's the same all the way along its length, all along its length. when the cable touches an object, it applies a force vector that first has a magnitude of T, so its magnitude is equal to that tension. Second is parallel to the cable. And third acts away from the object and toward the cable. So, for example, if okay, this guy's supposed to be like playing tug of war or something. The force that that cable applies to this guy is parallel to the cable, away from the guy and toward the cable, so that direction, and the magnitude is T. And so if you figured out the angle that that cable makes with the positive x-axis, you could use cosine and sine to represent that as a vector. You just multiply T times cosine and sine of whatever. The easiest way to think about this is when you choose an object that touches a cable, include a small chunk, let's say like a stump of the cable, with the chosen object. Then the force applied by the cable acts straight out of the stump. Okay, so for example, if there's a box that's hanging from a cable connected to the ceiling, and you want to find the force the cable applies to the box. There's the box. Include a little stump of the cable. And then the force applied by the cable comes straight out of that stump, and it has a magnitude of T. You also, in this case, would have the weight acting down, mg. Any questions about this yet? Okay, so let's do an example like this one. So let's say there's a hook connected to the ceiling, and a cable is attached to the hook, and a 10-kilogram object is hanging from the cable. So first, what's the cable tension? And second, what's the force vector the cable applies to the block? Well, I'm going to choose to isolate. My chosen object is going to be this 10-kilogram block. And I'm going to also include a little stump of that cable. So the forces acting on it are a downward force because of the weight. It's 10 kilograms times 9.81 meters per second squared. So 98.1 newtons. And now the only other kind of force is you're looking for contact forces. The only contact force is the cable. So that acts out of the stump with a magnitude T. I'll use a coordinate system like this again. So Newton's second law, what are the components for the weight force? Yep, 0, negative 98.1, because that's in the negative y direction. And what are the components for the cable force? You see that cable force is acting in the positive y direction. So that's just going to be 0 for x, positive t for y. That's all the forces. And then that's equal to the mass, 10 kilograms, times the acceleration. What's the acceleration of this box that's hanging there? Yeah, it's not moving. It never has any velocity, so the velocity is never changing, so the acceleration is 0. And so now I can break this up into an x equation. The first one says 0 plus 0 equals 0, and that's good news. Yeah, exactly. That's undeniable. It doesn't really help us solve for anything, but it's just reassuring. But then the second equation is the useful one. It says negative 98.1 plus t is equal to 0. And that's just an algebraic equation we can use to solve for t. We get that t is equal to, add 98.1 to both sides. T is equal to 98.1 newtons. So for part A, the cable tension is 98.1 newtons. Part B now asks for the force vector that the cable applies to the box. So what it's asking for is now when you plug 98.1 into this vector or into this vector, it's the same thing. What's the vector you get back out? So the easiest way to do it is just take this value, 98.1, and plug it back into the vector that represented that cable force in Newton's second law. So for B, this is the force applied by the cable. So plug T equals 98.1 into 0T, and you get 0, 98.1 for the force vector. So what direction is that force of 98.1 acting on the block? Up, yep, in the positive y direction. And one thing you can always look for, if this ever doesn't happen in a problem, something went wrong with the problem, the cable tension T is always positive. Now, the vector components don't have to be positive, but when you solve for that variable t, those always have to be positive or something went wrong. Okay? So it's sort of a sanity check you can do if you ever get negative 50 or something went wrong. Okay, let's do one now where we have cables involved. Okay, so you have a cable that's holding up a 5 kilogram mass. It goes over a pulley and then connects to the wall. What's the force vector the cable applies to the wall? So we're going to choose that 5 kilogram block to look at with Newton's second law. And since there's a cable attached to it, we'll add that little stump of cable. And then the forces are a downward force of 5 times 9.81, which is 49.05. And then the cable force comes right out of the stump, has a value of T. So Newton's second law. The weight force, what are the components of this 49.05 force? Yeah, that's in the negative y direction. We choose this coordinate system again. So 0, negative 49.05. And what are the components for the cable force? 0, positive t, that's in the positive y direction. And that's equal to the mass of the block times its acceleration. If this cable is just hanging here, there's no acceleration. So this is 0, 0. So the x equation says 0 plus 0 equals 0. Yay! Right again! Sometimes you do these and you get 50 equals 0 or something, and then you're not so happy. And then the y equation says negative 49.05 plus t is equal to 0. Solve for t. T is equal to 49.05 newtons.
Sorry, could you real fast just go through the Newton's second law and explain what the different component, things represent?
Yes. So you have to think about one by one each force that's acting on the chosen body.
Yeah.
So in this case, there's the weight acting on the chosen body. That's this. And then there's a contact force with the cable. That's this. And there's no other forces acting on it. So we're done. Once you've included the weight force and you've included a force for everything that's touching the body, you know you're done. Mm-hmm. And then that sum of the forces is equal to the mass of the chosen body times the acceleration vector of the chosen body.
Okay.
So that 0, 0 is the acceleration. It's hanging there. It's not moving. So, yep.
So the whole rig of it being attached to the wall doesn't have an effect, like it would be the same?
It doesn't have an effect, but now we're going to think about the wall because the question asks for what's happening at the wall.
And for the weight, could you please explain the x and y values? Why is the y value negative 49.05?
We know that it's acting this direction.
Mm-hmm. Well, I know why it's negative,
Okay.
but is it just because, you use the acceleration?
Yeah, this the weight is always equal to the mass times 9.81.
Okay.
So now we're going to use what we know and think about the contact with the wall. So I'm going to think of the wall. I'm going to include a little stump of the cable coming out of the wall. So the force that the cable applies to the wall is out of the stump. Do we know what the magnitude of that force is? It's T because all this cable's doing is, in the middle, is touching pulleys, and that doesn't change the tension. So we know that this is still T, and we know that T now is equal to 49.05. And so now we just have to express this vector in components. So if this is our coordinate system, the magnitude's 49.05. It's pointing in the positive x direction. So what are the components? Yeah, positive 49.050. Yep, exactly. Yes? In the x direction? Or why do we know it's in this direction? Because when what the question asks for is, what's the force vector that the cable applies to the wall? So now we figured out what the tension is in the cable, and that's true for the whole cable. And now our chosen body is the wall. We're going to think about the wall. And since the cable is touching the wall, we include a little stump of the cable in our chosen body. Yeah, so now we isolated the hanging block just so we could get this value that represents the whole cable. And then we isolated the wall, and the force applied to the wall comes out of that stump. And so now we know the force direction's that way, and we can just think about it as a vector.
You're just going off of the picture that you drew the first time?
Yes.
Where the pulley is pulling it directly horizontal, not
Yes.
going up at all?
That's right.
If the picture was different, though?
You're right. It would, yep.
Okay.
That could, if that was a 20-degree angle or something, we'd have to think about that angle.
Okay.
Any other questions right now? Okay. So here's one I'd like you to think about for a second. See if you can work through this together. So now we have an elevator. And it has an upward acceleration of 1 meter per second squared. And inside the elevator, you have a 2 kilogram mass hanging from a cable. What's the tension in the cable? Okay, so did anyone get through it? Okay, good. So for the chosen body, we'll choose the 2 kilogram block. And it's connected to a cable, so we'll include a little stump of cable. The downward force is 2 times 9.81, so that's 19.62. And then the only other force is the contact with the cable, so that's out of the stump, like that. And then Newton's second law says the weight force, 0, negative 19.62, plus the cable force, 0t, is equal to the mass of the box times the acceleration vector of the box. It's accelerating in the positive y direction, so that's 0, 1. The x equation says 0 plus 0 is equal to 0. And the y equation says negative 19.62 plus t is equal to 2. And so t is equal to positive 21.62 newtons. What would be the tension? Question?
I was going to ask, was that 19.62 given?
That's the mass of 2 times 9.81. So you're given the mass, and you just multiply that by 9.81 to get the weight. What would the cable tension be if it wasn't accelerating? 19.62. And so when this started accelerating upward, you needed a slightly stronger cable to hold it up. Any other questions? Okay, so all this back to about, one more thing I want to say about cables is not really cables, actually, now that, let's say one more thing about pulleys. I only bring this up because I remember when I took my first physics class, this was confusing for me because I had always heard about Pulley Advantage, the ability of pulleys to reduce the amount of force that you have to apply to things. And then what we see when we do the physics of a pulley is all a pulley does is change the direction of the force that the cable applies to things. All it does is change the direction. So all a pulley does is change the direction of a cable force. So does that mean there's no such thing as pulley advantage? Well, there is, but I would say don't think of that as a property of the pulley itself. There's a way to rig up pulleys so that you get that effect, but a single pulley doesn't do that. Pulley advantage comes from a specific arrangement of multiple pulleys. Not from a single pulley. And I want to just draw this picture. We don't have to go into the calculation, but so here's like a comparison. So first over here, let's say that you have one pulley hanging from the ceiling, and a cable goes over the pulley, and on one end, let's say you have a 100 kilogram mass, and you want to know how much force you have to apply to that cable to hold that up. So to hold this up, this one we can do the calculation for. T is equal to 9.81 times 100, so 981 newtons. So now let's do a similar setup, but this time the 100 kilogram mass is attached to a pulley that hangs from the cable. And another cable goes all the way through this system of pulleys. Can you picture what's going on there? Any questions about that? Now, how much force, how much cable tension do you need to hold this weight up? This is surprising, cool. T is equal to 490.5. Okay, so that's pulley advantage, but it doesn't come from a single pulley. It comes from rigging a pair of pulleys up this way. And actually, you can rig up, if you have more pulleys, you can get even more pulley advantage from it. But any old pulley doesn't do that. If we're ever in lab and we have extra time and you want to increase the amount of time that we sit in lab, which makes it sound unlikely that you're going to do this, but let me, it takes 2 minutes to take a couple of the pulleys we have in lab and hook it up to a mass and set this up, and you can do it and you really feel it, you know, like you hook it up to get this pulley advantage. You can hold this string really lightly and hold up a much heavier weight, you know, sort of cool. Any questions about pulley advantage? All right, everything we've been talking about, all the way back to here, has to do with, yeah. If you do it in a very specific way. I think every time you add, you have to add 2 pulleys. You have to, yeah, it has to be an even number of pulleys and it has to be in a pretty specific configuration. But then it just keeps cutting it in half, yeah. Okay, so for most of this class we've been talking about the direction of forces produced by pulling with cables. So now we're going on to the second one of these, which is frictionless contact along a flat surface. I think what I called it before was pushing contact along a flat surface. So some examples of this are if you have a box sitting on the ground and you know that the contact is frictionless, or at least friction isn't going to affect how you treat this problem. Or if you have something on wheels in contact with the ground. Or say you have 2 objects rolling on the ground and they're in contact, then this would be a pushing contact along a flat surface. This is pushing contact along a flat surface. This is, and this is. Okay? Those are all cases where things are pushing against each other along a flat surface. So when the chosen body is in pushing contact along a flat surface, then the contact force is perpendicular to the flat surface of contact. Perpendicular to the surface of contact. And second, it is toward the chosen body. Away from the contacting body. Okay, so when you have a pushing contact, that force is toward the chosen body, away from the contacting body. When we were dealing with pulling, that pulling force was away from the chosen body toward the cable, the contacting body. So the directions of those forces are opposite, which makes sense if you think about the difference between pushing something and pulling something. You're just switching the direction of that force. Okay, so let me do an example. So let's say you have an object on wheels. Let's say the mass is 20 kilograms. And we want to know what's the force vector applied to the, I'll call it a cart, by the ground. Well, the chosen body is the cart. The forces acting are a downward force of mass times g, which is 196.2. That's gravity, and now we have to deal with the contact forces. And the only contact is a pushing contact from the ground along that flat ground. So the force is perpendicular to the ground, toward the chosen body, and you can give that any variable you name you want. I'll call it n for normal. Normal means perpendicular, so a lot of times people call these normal forces. And now Newton's second law says, if we use this usual coordinate system, the force applied by gravity is 0, negative 196.2. That normal force is in the positive y direction, so that's 0, n. and then that's equal to the mass times the acceleration. We're just imagining this thing sitting here. And so the x equation again says 0 equals 0. The y equation says negative 196.2 plus n is equal to 0. Solve for n, and you get that n is equal to positive 196.2. And so then the force vector applied to the cart, you can plug this value back into here. So this is the force applied by the ground. We solve for n, so plug that value back in here, and you get 0, positive 196.2. Any questions about that? Okay, let's stop there. So remember, the lab test is next week, so spend some time reminding yourself about that stuff.